Hi everybody, this video is on section 3.4 about linear programming, which is the method for finding a minimum and or a maximum value of some quantity given a set of constraints. And constraints are what forms your system of linear inequalities. The graph of your solutions is the feasible region. It contains all the points that satisfy all the constraints. And a lot of times you're going to use that objective function. And what that does is it's a model that allows you to try and find that maximum or that minimum value. And if you have a maximum or minimum value of your objective function, it's going to occur at the vertices of that feasible region. So you can solve a problem using linear programming by testing all the vertices of your feasible region using that objective function. So some of the vocabulary that you're going to use for this linear programming discusses constraints, feasible region, objective function, maximum, and minimums. So let's just go ahead and jump right into it, and let me show you what that looks like. So here's three problems that we're going to use, and let's start with this situation number 1. And it says the owner of Fred's Fish Market orders cod and salmon. He wants to buy at least 50 pounds of fish, but he can't spend more than $300. Those would be your constraints. Cod is $4 a pound, salmon is $7 a pound. X is going to represent the number of pounds of cod, and Y is going to represent the number of pounds of salmon. So for this inequality, one of the first things that we've got to do is write the equation given the constraints. So let's take a look at that sentence where he says he wants to buy at least 50 pounds of fish but cannot spend more than $300. All right, so basically you've got a amount in pounds kind of problem, inequality, and a money problem for that inequality. So I'm going to go with the 50 pounds. He wants to buy at least 50 pounds of fish. So that means between the pounds of cod, which represents the X, and the pounds of salmon, which represents the Y, those two together have to be at least 50 pounds. So that means 50 pounds or more. So my inequality is going to be greater than or equal to 50. So then we go to this $300. I can't spend more than $300. So that means I can spend $300 or less than that. Let's see. The cod is $4 a pound, so that's going to represent our 4x. And the salmon is $7 a pound. So if I add to that the $7 a pound, and it's got to be less than $300. So here's my two inequalities. So I need to be able to graph these inequalities. So for this inequality, x plus y greater than or equal to 50, a lot of times I end up using the x and y intercepts. So the y-intercept is when the x value is 0, and I plug in that for x, and I get y is greater than or equal to 50. So the y would be 50. And then for my x-intercepts, I'm going to plug in y is 0. And when I do that, I get 50 for the x. So I'm going to go ahead and put a point at 0, 50. And I'm going to put a point at 50, 0. And and it is greater than or equal to, so it is a solid line. And its shading is going to be greater than this boundary. So then after that, I am going to graph this 4x plus 7y less than or equal to 300. So using my x and y intercepts, my y-intercept, if I plug in x is 0, gives me 7y less than or equal to 300. Take 300, divide by that 7, you get right around 42.86-ish. And then to find the x-intercept, I'm going to plug in 0 for y. I get 4x less than or equal to 300. Take 300 divided by 4, and you are going to get 75. So to graph that, my y-intercept is 0 and 42.86, so that'll be right around here. And then my y-intercept, or my x-intercept is 75, 0. So this is where I'm going to just give a little sketch here. And this is where it is less than or equal to, so it's going to be shaded below. So what happens is that you get this feasible region right in this area, right in here. Okay, so your feasible region, and it's going to have vertices, and those vertices are the boundaries of that feasible region. Okay, so when it goes down here to the problem, it says which of the following are solutions. You're looking for solutions that are going to be in this feasible region. So that would mean this 40, 15. The 50, 18 is not in that feasible region. And then the 30, 20 is. 55, 8 is. And 20, 35 is not. You can also substitute in, for example, this 40, 15, plug in x is 40 and y is 15 into each equation. It has to satisfy both equations in order for it to be a solution of this system. And you can do that for each one of the next coordinates. So there's the first part. This situation number 2, flower power, says Mr. Bloom is designing a rectangular flower garden with a fence around it. He can use no more than 80 feet of fencing, so there's a constraint. He wants the width to be at least 5 feet and the length to be at least 20 feet. So here's what I know. The first constraint, if x represents the width of your garden and y represents the length of your garden, I can use no more than 80 feet. So that means 80 feet or less. I'm going to have two widths. So that would be 2x. And then I'm going to have a 2y, because I'm going to have two lengths. And I can't use more than 80. So that is 80 is my max there, so less than or equal to 80. And then for inequality number 2, it says he wants the width to be at least 5 feet. So that means x has to be greater than or equal to 5. And the inequality number 3 says the length to be at least 20 feet. So that would mean y is greater than or equal to So that would mean that y is going to be greater than or equal to 20. Now I'm going to graph this first inequality, I'll go ahead and do that in red. And again, I'm going to use my intercepts. So those would be the y-intercept is going to be 40, and the x-intercept is going to be 40. And it is going to be a solid line. And the shading is going to be below. Okay. I'm going to use green to do this next one. X is greater than or equal to 5. So notice that the increments are in 5. I'm going to have a solid line and shading to the right. And then I'll use purple for this last one. And y is greater than or equal to 20. That's going to be a solid line. And greater than is going to be above. All right, so bottom line is this. The feasible region, which I'll do, I'll just choose black for that. The feasible region is this region right here. That is my feasible region, okay? It has vertices. Right there. And those vertices are going to be 520, 2020, and 535. So it says, which are the solutions? The solutions are found in that feasible region. So if you look at 1023, that lands in the feasible region. So it's a solution. 730 is a solution. It lands in the feasible region. And then 1825 does not. 835 does not. And 2020 is in that feasible region because it is one of our vertices. Now, hopefully you understand what the constraint is, what a feasible region is, and the vertices for our feasible region. So let's take a look at this application problem, and it's going to take us through where it has two constraints, and we're going to have to graph it in order to find our vertices. And then once we find the vertices, we're going to use that objective function in order to find the maximum profit. All right, so here we go. It says, What's Up Toys is a small toy company that specializes in toy cars and toy trucks. The people at What's Up Toys are confident they can sell all the toy cars and trucks they make. But there are two constraints that limit their production today. Wheels and seats. Those are your two constraints. All right, so it says each car needs 4 wheels and each truck needs 6 wheels. So it says X is for cars, Y is for trucks. All right, so that would indicate for the wheels constraints that a car needs 4. So that's going to represent the 4X. And the truck needs 6 wheels, so plus 6Y. And I have 360 wheels in stock, so I have to use less than or equal to 360. All right, there's my first constraint. And then the second constraint is seats. Each car needs 2 seats, so that's going to represent a 2X right there. And truck has 1 seat, so that's going to be plus Y. If you'd like to put a 1Y, that's fine. And it has 100 seats in stock, so that means I could have at most 100 seats, so less than or equal to 100. All right, there's my two constraints. All right, I have written the two inequalities based on those constraints. So I have to find the intersection of the inequalities to show all the combinations of the cars and trucks. that they can make with these two constraints that were given. So I'm going to go ahead and graph this, and again I'm going to use the intercept method. So I'm going to have the y-intercept, I'm going to plug in 0 for x, so that would give me 6y less than or equal to 360. 360 divided by 6 is 60. All right, so the y-intercept is 0, 60. And then the x-intercept, I'm going to plug in y is 0. That would give me 4x less than or equal to 360. Divide by 4, that gives me 90. Alrighty. And then I'm going to also use the intercept method here for this second inequality. So my y-intercept, when I plug in x is 0, it's going to be 100. And then the x-intercept, when I plug in y is 0, is going to be 50. All right, so here are my two equations. So I'm going to do this first one in red, and then I'm going to do the second one, we'll just go blue. Okay, so this first one is going to be in red. So I'm going to graph the intercepts. I'm going to graph 0, 60 and 90, 0. So guys, one of the best things you could do is probably use a straight edge. I'm going to have to go by hand here. It makes it a little bit tougher to help to find those vertices, but I will do the best that I can here. All right, notice it is solid because it is a less than or equal to. So when I graph that and I have to shade now, I'm going to graph, or shade, sorry, below. All right, so I'm going to now graph the second inequality, the 2x plus y is less than or equal to 100. Its intercepts are 0, 100, and 50, 0. Okay, and again, probably best to use a straight edge for me. Unfortunately, I'm going to have to do a little hand draw here. All right, that's not too bad. And it is less than or equal to, which means I'm going to shade below. All right, so this brings me to my feasible region. So my feasible region, I will do in green. My feasible region is looking at where all these vertices are. I will circle these vertices. All right, and that is my feasible region. So everywhere where these two functions intersect is going to give me a vertex. And this is my feasible region. So the feasible region is going to give me some vertices. And I'm going to list these vertices, and I've got 0, 0, and I have 0, 60, and it looks like I have 30, 40, along with 50, 0. At this point, I need to write my objective function, and that objective function comes from this information here at the bottom. So let me write objective function. All right, so it says suppose the profit on each toy car or truck sold is $1. How many cars and how many trucks should What's Up Toys make in order to maximize profit? So in other words, my objective function is profit equals 1C, 1 car. I guess I shouldn't use C. I'm going to have to use X. So 1X plus, I make $1 off the truck, so 1Y. All right, so my profit, when I plug in 0, is 0 plus 0, and that is 0. When I plug in 0, 60, I'm going to 0 plus 60, and that is 60. If I plug in profit here is 30, plus 40. Plugging in both those x and y's, I'm going to get 70. And here the profit is 50 plus 0, and that is 50. All right, so the key thing here is to notice I'm looking for maximum profit. So my maximum profit is going to be this largest number, 0, 60, 70, or 50. The largest profit is going to be $70, and that happens when we make 30 cars and 40 trucks. So given the constraints for our wheels and our seats, we were able to evaluate, write some inequalities, and check out those vertices of the feasible region in order to plug those vertices into our maximum profit equation in order to figure out what's best to make what's up toys make maximum profit. All right, I think that's all I have.